Okay, still 161 games left. Uh, anyhow, let's not look at these stats because there's only one game's been played. So let's look at the 2025 stats, right? So for those who don't follow baseball, the Dodgers and Yankees are very good teams. Dodgers won the last two World Series. Um, they have a lot of really good players. They spend a lot of money. So sometimes you kind of wonder, well, what stats can we use to correlate with victories, right? Because what's the objective of baseball? To win a game, to get the most wins, make the playoffs, and then win the World Series, right? That's the objective of any sport, right? And sometimes if you look at the stats, like for those who don't play baseball, maybe play soccer, maybe play basketball, maybe play football, water polo, whatever it is, right? Um, Sometimes you look at like, oh, how many goals did like Sigerhart score, right? Or how many yards did Sigerhart get? Like sometimes you could use those correlations. Oh, Sigerhart leads the league and or leads whatever you guys plan, right? Um, and yardage, whatever. So if we look at last year, let's look at home runs, right? So who were the league leaders in home runs? Like you see, okay, Yankees are number one, Dodgers number two, and so forth, right? Um, but it's interesting because you look at some other teams that are kind of in the middle. Um, like the Giants were, well, no, they're not like totally in the middle, but there's some teams that, okay, Athletics is a great example. Athletics were not very good last year. They're now up in Sacramento, right? But they probably hit a lot of homers because it gets really hot in Sacramento and the warm air tends to carry the ball, right? But they didn't do very well, right? So it kind of begs the question, can we use this to correlate with victories? So what I did was I just took a copy and pasted the data, and the data is a bit of a pain in the ass because you have to copy and paste, and it doesn't really come out very nice sometimes. So let me show you what I did here. So what I did is I ranked the teams. Well, I ranked them, I sorted by alphabet. So I took Arizona Diamondbacks all the way down to Washington Nationals. Put the home runs in one column and the wins in another column. So, for example, it's the Athletic. They have a great season. They won 76 games. Usually winning 90 to 100 games is considered good. The Cubs made the playoffs. They won 92 games. They did a lot of homers, right? If you look at some teams that were kind of crappy, Washington was not very good. They had 161 homers, right? They only had 661s, right? So, is there a correlation, right? Um, and what happens when you do correlations? There's something called independent and dependent variables, and we'll talk about in the worksheet. There's independent and dependent variables. Independent, what letter do I use? Will I use X or Y? What do you guys think? X, yeah. Independence usually X. So you choose that. That's your choice. Dependent is going to be Y. So what I did is I let home runs be X and wins be Y. So what I'm doing, or sometimes we call it we call Y the response variable. And we'll talk about this when we do the worksheet. And we'll call X the explanatory variable. So for those who are taking AP Stats next year, any juniors think about AP Stats next year? Are you taking? Oh, so then you already know what I'm talking about. Yeah. Um, and I'll try to do as good a job as Kamo does with this stuff. So explanatory, right? So can we use home runs to explain the wins? And the wins respond to the home runs, right? That's why we call it the response variable. Y responds to X. So, for example, you could say, "Hey, maybe I'm checking for me personally because I'm 48 and I got to watch my weight, how many calories I take in, right?" So the calories would be the explanatory of my weight would be the response. My weight would respond to how many calories, or from working out. Like if I decide to go for a jog for 30 minutes, maybe I increase my time. I could use the time for my jogs to explain my weight loss, right? You could do all those things, right? So if we look at it, the correlation is not that great. You can see like it. So this is called a scatter plot. We call it a scatter plot, which will generate in the worksheets, because what you're doing is you're trying to plot all this data. So I have the wins. Um, Actually, I had it reversed. Yeah, shoot, that was terrible. Um, that's okay. It should be the other way around, but it's all right. We'll deal with it. Um, I should have had the wins on the y-axis and the home runs on the x. I don't know what the heck happened there. Whatever, it's fine. But you can see it's all scattered, right? So it's not a very strong correlation. We probably draw a best fit line, but you can see some of those are outliers, right? Now, do you guys know what outliers are? We're outliers. Or why we call go everyone explain to us?
Yeah, well, I'm a second. It was like they're outside the interquartile range, so like
Mhm.
Q1 and Q3.
Right. They're unusual. They're very unusual, right? So like this one here, I wouldn't say it's totally unusual. I mean, a team hit 274 homers and got 94 wins. But you look at this, like this team here. Um, actually, let's look over here. So this team didn't hit many homers and got 90 wins. Can't remember what team that might have been Cleveland, perhaps. Um, trying to figure out what that data point is. But it kind of begs the question, okay, there are teams that were very successful, or this team, right? Okay, actually, this is a great example. Actually, this is a fantastic example. So what gives? So this team had 274 homers, had 94 wins. This team had like way less, 106 wins, had 97 wins. Okay, what team was that? Right? So that's the beauty about statistics is sometimes it tells you a story and then you figure, wait, let's dig a little deeper. Okay, Milwaukee, great example. Milwaukee had the best record, almost went to the World Series. The Dodgers thought, actually, if you guys who did follow baseball, Shohei Ohtani, very famous Japanese player for Dodgers, absolutely demolished Milwaukee. One person hit 3 homers and like shut him out as a pitcher as well. But regardless, what gives? Why are they? What? How did they get so many wins but didn't hit many homers? The other thing I'll look out for as well is a variable called R squared, which stands for the correlation coefficient. And Avery, do you want to explain R squared?
It's just how well the dot, like the line fits the dots, like how close they are to the line.
Right, and also how well we can use the what percentage of the variation in data can be explained by the explanatory variable. So you got to write like that line
Yeah.
AP, by the way. Okay. Um, so about 15.5% of the variation in data could be explained by the home runs. Okay, but can we do better, right? Can we do, can we find a stronger correlation? So if we investigate Milwaukee, what made Milwaukee so good? For those who follow baseball, Milwaukee have phenomenal pitching. Now, in sports, sometimes defense matters more than offense, right? So in soccer, defense matters a lot. Actually, Mr. Davison's daughter, Terrence, she's a phenomenal defender. She did very well, right? She did play last night. Cool. That's great. She's back, right? Or in football, like a good defense can get you very far, right? Seattle had a great defense and they beat the crap out of us in the playoffs, right? So if you look at Milwaukee, now there's another stat called ERA, which stands for earned run average. This is a metric we use for pitching, right? So a lower number is actually a good thing. It means you're not allowing many runs. If you have great pitching that the team can't score, you probably win the game, right? You just need to score a few runs. So now let's look at the teams that are crappy. Washington had a very high ERA. Colorado, by the way, why is Colorado unique compared to a lot of other baseball stadiums or baseball cities? What's special about Colorado? At high elevation. What happens when you're high? For those who take physics, what happens when the elevation's high? You can't breathe, and also the air's thin. The air's thin. What happens to the ball? Does it travel further or long or shorter? Further, because there's not as much resistance, right? So you're gonna have a lot of homers, right? And they only won 43 games. That's terrible, right? Now look at this correlation. This correlation is very strong. Okay. That's 0.598. So 59.8% of the variation can be explained by how well your pitching does, right? And so you see there's a very, and also look at the data points, a very tight along that line, right? So this is the beauty about statistics that you can start using this to start understanding data, right? Like, oh, why do things happen? Sports is great because sports is very rich in data, right? Now, I'm gonna get a little political before we do the worksheet. I did this about 5, 6 years ago when there was a national reckoning of race, there was COVID and this and that, and I was teaching IP stats, and but my stats students were just so checked out, like so. It was like talking to a void on Zoom. It wasn't fun. But here's what I did. And King C might like this because I know you do the US civic stuff. Okay, first off, let's look at the presidential election in 2020. So Biden beat Trump. Of course, Trump was very upset about the election. He looks upset in that picture. And of course, some votes, our country's very divided. So we see a lot of red in the middle, right? We're here. We're very blue, right? And blue pockets like in the Northeast. Somehow we got, and we got, some of the Rust Belt states, right? And of course, Trump complained about the election, right? But what I want to look at more so is how each state voted. Some states were Trump heavy, some states were Biden heavy. Alabama, very Trump heavy, right? California, very Biden heavy. But then I just had this hypothesis, and this is the beauty about statistics and science, that you come up with these hypotheses, right? Like, oh, okay, well, is there a correlation with how people voted and COVID? This is where I'm getting a little political now, right? And I started feeling this way because you guys remember, well, you guys are too young because you guys were in middle school, but if you had any older siblings, did any of you guys have any older siblings that had to travel out of state to take the SAT, or you guys know anyone who? So during COVID, you couldn't take the SAT in California because of our strict restrictions, right? So I knew a lot of students who were flying to Idaho, flying to Arizona to take the SAT. And why were they able to take it there, not here? Because they didn't have the COVID restrictions. Those states are also very conservative. They tend to vote for Trump. Idaho. Let's look at Idaho, right? I have a very good friend of mine. He lives in Idaho because he cannot stand living in California. He's very conservative. Fine. That's who he is. Arizona is kind of in the middle a little bit, right? So I figured, hey, let's look at the COVID infection rates. So what I did is I looked at the mortality rate. Now, not the deaths, because that's a little bit tough to look at because let's see, let me download. There we go. Perfect. That's what I want to do. It's hard to look at the straight up number of deaths because California has more people, right, than most states. So it's better to look at a rate, the number of deaths per divided by the population. So sure, California had a lot of deaths, but look at the death rate. It's pretty low compared to other states, right? But some had really low ones, like Alaska and Hawaii. Why would we think Alaska and Hawaii be so low? They're so far away, right? And Hawaii was very strict. Like you couldn't get into Hawaii. They were so strict with their quarantines, right? Um, Now let's look at New York, right? Well, New York was high. The death rate was high. But why would New York have a higher death rate? Because it's very dense, right? New York City has a lot of people living there, right? Um, but then you can look at impoverished areas. New Mexico tends to have a very high Native American population, very impoverished. So it's interesting when you look at the data, right? But then you look at like, okay, Mississippi, they're very red. So I started thinking to myself, Kentucky. My wife went to grad school in Kentucky. She tells me how conservative it is over there. Okay, like you start seeing these things, right? So I just kind of wondered, well, I don't know what gives, right? Like, is there a correlation with how people voted and the COVID death rates? This is where I'm getting a little political now. So sorry if I offend you. I don't mean to do that, but I'm just curious, right? Um, by the way, let's look at South Dakota. South Dakota's pretty high. Who was the governor of South Dakota at the time? Thank you. And she's that whole wackadoodle who was at the Department of Homeland Security got fired, right? So again, I'm getting very political, right? Um, West Virginia, very conservative. I love the song. It's a great song, right? But in Texas was like kind of normal, right? So Utah is also very conservative. They're also kind of low. So let's look at the data, right? So I did a correlation. I think I did over here, and not a very. It's all over the map, right? No pun intended, 'cause I did look at the map, but if you think about it, fine. Alabama, that's the percent of people who vote for Trump. So I use this as an explanatory variable. I use this as a response. How does COVID death respond to how you voted? Is there a correlation? Not really, actually. So hopefully, if you're conservative, yeah, I'm not offending you because there's not much. So, but it's worth a look at, right? That's a very low value. It's close to zero. Now, this close to zero, that means it's really just scattered. It truly is. It's very random. So anyway, I didn't see anything there. Now, I haven't had a chance to do this yet, and maybe we could do it if we have time. But maybe we could look at COVID death rates again. Forget about the politics now, and U.S. life expectancy. So, for example, California has a pretty high life expectancy. Maybe we could do that correlation a little later. I looked at 2019, right before COVID. California's going to be healthier. Why? We have a beautiful weather here. If you look at San Francisco, you hardly see any obese people in San Francisco. Why? They walk everywhere. They have like vegan things everywhere, right? They're into yoga and things like that. So, or LA, LA is beautiful. Hawaii people are very happy. They're not stressed out. Um, but if you look at, I'll go back to Kentucky again. Again, my wife went to grad school there, but she told me they have all these, the healthiest restaurants in Applebee's, right? They have these greasy spoons everywhere. They have high diabetes, high heart disease. Um, Massachusetts, highly educated area. They're probably more in tune with their health. Um, but you also look at if we want to get social here, let's look at Oklahoma. Oklahoma is one of the highest Native American populations. Probably not access to healthcare, right? That could be another thing to think about. So, oh, okay. Right. Anyhow, I'm very passionate about this stuff. I think this stuff is fascinating. Um, and just so you know, linear regression is a very crude way to look at stuff. You really want to use more types of regression. So we're also going to look at exponential regression, other types of regression that might be more reliable. So I'll get off my soapbox here. So now let's actually look at the worksheets, right? And so let's actually get our hands around the data. So you and a partner are going to do this together um, because it's just going to be easier. And you're going to need a laptop too. So you definitely need a device. You're going to use Google Sheets. I'm going to walk you guys through the first example, and then we'll keep going with other stuff as well. We're going to use Desmos. Actually, let me take it back. Let's use Desmos instead of Google Sheets. Yeah, thank you for correcting me. Because Google Sheets is going to be a little tricky. Let's use Desmos instead. Desmos will be better. I agree. Let's use Desmos. Thank you, Charlie, for correcting me on that.
If
Was that? Oh, I didn't update it. I'll take care of it. Yeah, thanks. Okay. All right, so let's look at the first example. Let me pull up the one on linear regression. Oh, by the way, yeah, for those who do their notes, does anyone want to do these notes online too? Yeah, let me post the Schoology first. Give me one sec. Let me put the notes online. Pull up also.
Make it on Saturday and say no to intervention. 32626.
Okay.
So the class and the. Oh, no. Or the. After you do your lines.
Yeah, let me upload this to Schoology also, so you guys have access to it there. I'll just put in the main page for Schoology.
Mr. E, which one are we doing?
We're gonna do linear regression first, and we're gonna do it on Desmos.
Okay.
I just gotta upload the
worksheet.
Yeah, but I'm gonna walk you guys through it though for the first one at least.
It's like a height split, not like a. Oh, it's like a. Okay. Okay, yeah, because it's really not that. Okay. Let's be like, oh, and then we send that. Yeah, so the height, because.
All right, here we go. Sorry for a little delay, guys. All right, so if those who want to do notes online, you can. All right, let's go to Desmos. So I'm gonna type in table. Okay, we know X1 is gonna be high temperature. X and then Y1 will be number canceled. So what's our hypothesis here, right? When it's hot outside, people buy more soda because you're thirsty, right? So when it's 84 degrees Fahrenheit, you might sell more canned soda. So it's a very simple example. Fine. You have a convenience store, you have the cooler or the refrigerator, whatever. So I'm going to type in all the data. So you may want to have one person do the typing and the other person do the writing, however you guys want to do it. 58,335, 64, 410, 68, 460. And just, this is a very rudimentary way of entering data. For those who are coders, you could totally scrape data. If you do run certain scripts, you could just automate it really easily where it could just if you are familiar with the whole API world, you could totally just do that yourself. Okay. Now I see my data. So my data's right here, right? If you ever want to change the window, because the normal window wasn't showing anything, because X is representing temperature, which are 2 digits, Y is showing Kansas soda, which are in the hundreds, 3 digits. But I could always alter my data however I prefer. So if we're looking at temperature, right? I'm not going to be looking at 0 degrees Fahrenheit. That's kind of crazy. Maybe we'll go from like 40 to 100. That might seem reasonable. And maybe I'll do the step as 10, every 10. Soda, it's going from like 300 to 800, so I'll go 300, 800, that's fine. And I'll do every 100, I guess, for that. Okay, so here's my scatter plot, right? And I can zoom out just a tad. All right, so part A is done. I already did the scatter plot, right? Don't do it by hand, that's crazy. We have technology for us. And thank you, Charlie, again. Desmos can be much used in Google Sheets. Google Sheets can be a little bit, you do have a little more features you can use in Google Sheets, but I think for our purpose, Desmos is fine. Now, this is graph the linear equation, right? Now, to do this by hand, and Avery, did you guys ever have to do this by hand in AP Stats? No, okay, good. I used to do it when I took stats many years ago, and it's a pain in the ass, right? So what's better is use the technology, right? And for those who are also taking SATs, you guys might be aware of this feature in Desmos. You could add regression lines. Now, if you add a regression line, it's going to do a line. Now, you could do a quadratic regression or other types of regression, but line's going to be good for us. You see the line looks pretty darn close, right? Also, the R squared value. Now you guys know with R squared. That represents your correlation, right? So you could say 93.5% of the variation, the data here, of the Kansas cell can be explained by the temperature. Yeah, when it's hot outside, you sell more. It's cold, you don't sell more. Simple, right? And what's my equation? My equation is going to be this. Y equals 16.4 X minus 621. That's funky because are you going to sell negative 660, negative 621 cans of soda? No, right? That's not going to happen. But for my range, or my domain, 300 to 800, well, actually that's a range, 300 to 800, right? 16.4. Now, how do we interpret that? So we're going to talk about that in just a moment. But that's your equation. That's part B. So part B is done now, right? We've done part B. Now use the model to predict 95 degrees Fahrenheit. Fine. Whatever. Let's plug in 95 for X and work it out. And we have Desmos, so we can just punch it in, right? So if I just punch that in straight up, so I could do 16.4 times 95 minus 621. Okay, so I should sell 937 cans of soda. There we go. But here's the thing is that there's also a limit too, because you can't have like 150 degrees Fahrenheit. We would die, right? So there's a bit of a limit sometimes. So we have to be mindful about that. One thing we do want to interpret really quickly is the slope. So part C is done for us too. 937 cans. There we go. And part D is where you actually could do the scatter plot. We'll make a mention of the strength and form and direction in a moment. So I'll answer part D in one sec for you guys. But let's talk about 16.4. That's my slope, right? Okay, how do we define slope? Slope is what over what? Rise or run, change of y or change in x. So you can think of 16.4 over 1, right? Now, what does x represent again? This problem in the context? And what does y represent? So here's what I'm going to say. For each increase of temperature by 1 degree Fahrenheit, we sell an extra 16.4 cans of soda. Is it soda or whatever we're selling? Sure, soda, soft drinks. There we go. So you can use this as a way to predict what could happen if the temperature is this or that, right? So now, is it super accurate? Not really. Linear regression is actually a terrible way to do this. And just so you know, this is actually the foundation of machine learning. You hear often machine learning is this complicated thing. It's actually not that complicated at its core. It's really using statistics to model future outcomes. You're building a predictive model. Of course, machine learning, if you take it with Ms. Holman, you guys do some really crazy stuff, really complex stuff. Great class to take if you are eligible to do that sometime down the road. But yeah, that's really the basics, is learning how to build a statistical model to predict things. That's what we're doing. So the last part D, describe the association you see. Well, it's a positive association, right? So if I go back to the notes, and then you guys could do part 2 on your own or with your partner. So lastly, what would I say about the association here? So I'd say there is a positive association, or it's a correlation, that works too, between cans of soft drinks sold and temperature. You can also say there's a very strong correlation, and the association is linear. So the direction is saying it's positive, because it could be negative also. Like with baseball, if you don't allow many runs, we saw it was a negative slope, right? Because that's a good thing. You can win more games if you don't allow many runs. So you want a negative association for that. But yeah, totally right here. That's your direction. Your strength, you're saying, is very strong. And the form, of course, is linear. So using a linear regression, positive association, very strong correlation. That's how you want to say it. Okay. So go ahead and try number 2. Here you're looking at, not as exciting, your femur length and your height. Sure, there's a correlation there, right? So go and try that, and then we'll compare in a moment.
Really good. Really? I can't figure out what's like a good price. I mean, I think it's not probability it has to be really good. Yeah. I would say having and I would every time I look back at it. Yes. But then like you know, like it's not I know. There's some people who like master all like but then most of the time like I hate it. I know when I first see it and I'm like, all right. Have you heard of the Instagram? Have you heard of the Instagram?
Also that means they really not like so
Kidding. Absolutely.
Negative like yeah.
Yeah, I'm gonna do it too. I'm gonna freeze.
Or like water. I mean, these are the other things related to.
Okay.
No, that's not what you totally looks like. No, I just like an idea. Yeah.
Oh, it's a red wing. I don't know.
And then like they're like on the light, which would kill them off.
It's such a sus thing to be on but just like what if you don't know this person, I'm just like what? Okay. Well,
And it's the femur usually around what, 9:30 or 9:35? What's 30 is better? Okay, we'll do 30.
They're in my phone and then another car and it's for
And I'll just like changing them now. I don't know the need them.
Are you gonna watch them last week?
Of course. The Rock and Jock I didn't care for.
It was the last track.
I'm sure it was. What was the score?
27-23.
Oh, that's close.
But yeah, we were winning at one point when there's like a minute left.
Oh, that's gonna be tough.
So much fun.
Yeah, of course. Yeah.
Yeah.
And what's the afternoon?
Pretty good. Yesterday. Like,
Oh, dodgeball.
just doing it again, yeah.
Yeah.
Yesterday.
I don't know. I think only
It was like a random shooting pain. No, I just like I twisted it, but okay.
Okay, you guys should be getting 1.923x plus 80.68. And if you want to predict your height, if your femur is 58 centimeters, again, not a very it's like a boring problem. I actually really do not like this problem, but I think politics and sports are more fascinating.
Is this like our homework or is it notes?
Just notes, that's all. There's no homework at all. Let's see, you guys want homework or a break? Okay, good. No homework or a break. I mean, this is something I will like kind of just ask again. Like, we could probably have a discussion this later, but this is just more of a standalone thing for today. So the height should be about 192 centimeters, right? And then clearly it's a positive association, right? Positive. The form is linear, and that is very strong. That's a very strong correlation. So linear model still wins, right? Linear model is fine. It works. So you have your best fit line, you have your regression equation, and again, R squared. And calculating R is also a real pain. That's not something you do. So we just let the technology calculate for us. And why is it R squared? So R is the correlation coefficient. R squared is what we call variance. And so that's a different thing necessarily, but it's still a good measure. So again, it tells us the variation of data could be attributed to the femur length, right? So 93.28% of the variation in height could be explained by the femur length. All right. Now let's move on to the second worksheet. Okay, the second worksheet. Before we get too deep into it, let's just talk about all the different types of regression. So some regressions, so linear may not be a good idea, right? Exponential might be better. So during COVID, people are getting sick really fast, or even the flu. It doesn't have to be COVID, right? But COVID was a big one because we all experience it, right? Maybe, like 5 to 10 people got sick, right? And then 100 people got sick, and 1,000 people got sick. And actually, true story. You guys heard about that cruise ship that was docked out in the bay right before COVID hit? Like some people were stranded for about 3 or 4 weeks. My father was on that boat. He was on that boat. He was traveling to Hawaii with his brother and his brother's wife and his brother's wife's sister, whatever. And someone had COVID on that boat on the previous journey, so they had to turn around, and then they wouldn't let him dock. And actually, that St. Travis Air Force Base for about 3 weeks afterwards. So, but did it matter? No, because everyone got COVID anyway. Because what happened was during that time frame, around this time 6 years ago, the infection rate started spiking, right? People were getting sick really fast, right? So would a linear model have worked for that? No, right? Exponential probably would have been better, right? But at a certain point, you can't keep doing exponential because there's only so many people in the world, right? Eventually, it's got flattened out. So that's also going to be a logistic regression. We'll talk about that later. But exponential would probably have been a better model for that. Or let's look at the stock market, right? Does the stock market, like if you look at the last, and actually, Kingston, you're in that talk with Mr. Gerson, right?
Yeah.
So we looked at the S&P 500, right? And actually, we're going to talk about that when we come back from break. We're going to talk about financial growth.
those numbers to the compounding.
Yeah, great. No, totally, 100%. But if you think about the S&P 500, because they use that for the Trump accounts, right? Has the stock market grown linearly or exponentially since the Great Depression? If we start from the Great Depression, World War II, that time frame until now, how has it grown? Exponentially. Now, granted, it's not like crazy exponentially, but it's still an exponential model, right? It grows maybe 7-8% a year. So exponential would have been better to use to model that, right? So in this case, here we're looking at Harley Davidson, so publicly traded company, right? And we're looking at the closing price of the stock from 87 until now, or sorry, not until now, until 2003, right? And you can see it did really well, right? Now, this is also where you can start comparing it to politics, right? So actually, I think this is fascinating, right? So you look over here, 96 through 2000, right? What was happening during that time frame? I know it's well before you guys were born, but your parents would know. But who was the president at the time frame from 96 to 2000 for those 8 Bush students? Before Bush, in between the Bushes, Bill Clinton, right? Bill Clinton. The economy did incredibly well. In fact, this school's endowment and population improved a lot because a lot of people were making a lot of money here down the street, right? So that would make sense, right? And then around 2001, someone guess what dropped. So it dropped, right? So why do you think we saw a drop in the price? Right? What was happening globally around 2001? I was a young adult at the time. You guys were not born. 9/11. 9/11 happened, right? 2001. And also the war in Iraq, right? So the economy took a nosedive around that time frame. So it's just fascinating when we start looking at this stuff. But if you look at the data, linear will not cut it for us, right? We have to an exponential model. So what you guys are going to do is use an exponential model. So we'll punch in all the data. And instead of using 1987, 88, let's do 1, 2, 3, 4, 5, 6, 8, 9, whatever, right? And we'll type in the closing price. Once we do that, let's fit the data, put in a scatter plot, and predict, hey, what would happen in 2004? And interpret the value of K in the equation as well. So let's go and do that. Let's go and type it in. And again, it's not fun to do. Honestly, if I were teaching like a data science or AP stats type of course, I would give you the data file and let you analyze it. I would not force you to type it. That's just stupid. We don't do that in real life. You actually have a data file that you clean and then you analyze. And you can have like someone read the data.
I mean, I got like that. You just like 31, yeah, other sports. Yeah. Did you guys have fun? Screen, like,
Oh shit, what did I just do? Sorry. I just got mad at myself. Sorry about that. All right.
Not all of them, like, not all of us are gonna like start with it. Like, I know I have some. Hey, the girl who plays my position is currently a junior, so then she'll graduate and I come in that. But and like they've already told me like that's your job, so it's not trying to figure it out. It's a defender, but like you have to go up and back and up and she's the like junior captain. And so and there's it's not always like sometimes the captain
Okay. So hopefully if you have all the data plotted, or typed in, then you can plot the data and do the regression. And of course, we're not doing linear. And of course, exponential is not perfect because it does drop, so fine. But exponential for the most part seems reasonable. The R square value is solid. So 90.54% of the closing price, the variation of closing price of Plug Davidson stock, can be explained by the time frame, years. Because as years pass, you see an increase in the price, right? Now the crappy thing about this problem is that Desmos, I don't think half of the people are giving you the exponential model with E as a base. I have to maybe some research to figure that out. I think Google Sheets might. That's where Google Sheets is a little better, has more of the flexibility. Yeah. So the problem here. All right. Good luck to you guys. I look forward to it. All right. So how do I rewrite this to look like this, right? So if you think about it, 1.21844 is going to equal e to the k. So what our task is to be to make it look like this equation. Now the y sub 0 is initial value. Yeah. That stays the same. I don't touch that. Leave that alone. But instead of a base of 1.218, let's do a base of e. So what I'm doing is I'm doing a change of base. How do I change the base? I have to deliberately set this base equal to e to the k and solve for k. How would I solve for k, or what would I do? You guys remember from algebra 2? ln, yep. You get a natural log. Because that's how you rewrite an exponential equation as a log equation. So my k value, if I want to write as an e function, would look like this. Natural log 1.21844, which is 0.198, we'll say. So 0.198. So y would equal 2.03 times e 0.198. So 0.198 to the t power or x power. We'll say t. Or you can think of it like this. 0.198 is pretty close to 0.2, right? What would 0.2 be as a fraction? 1/5, right? Okay. And t's measured in what? What's t measured in? Years. Okay. Okay. So it's measured in years. So it seems that every 5 years, and then e, of course, is 2.7-ish, if you were to compute that. So it seems that every 5 years, we could expect the price to go up to be multiplied by 2.7, or by 270% increase in the is that right? Be 270% increase? No, it'd be more of we'll say multiply by 2.7. So the way you can interpret it, so if you look at part F, now to get the closing price of 2004, I mean, you guys know what to do now. You just type in 18, y equals 2.03 times 1.21844 raised to the 18th power. Fine. Now the price is $71. Fine. Which I don't know if that would be true or not. That seems kind of crazy, right? Because the price did come down. But that's part E, to predict the closing price. We already done all the other parts. We did part C already. We did part D already. So anyhow, but to interpret it, how do you interpret K? So you could write it like this. let me clear this and go back to the worksheet. Then we'll do the back page and we'll be done. So here's how I interpret it. I would say every 5 years, the closing price of Harley Davidson stock is multiplied by 2.70. Or there is a 170% increase every 5 years. Why did I say 170 and not 270? Yeah, because if it's 1, it just stays the same, right? Multiplied by 1. If you do 1.5, it's 50% increase. So you always have to subtract the multiplier by 1 to get the true percent change, right? So every 5 years, increase by 170%. That's how you want to interpret it. So I took the decimal, changed it to a fraction, and then realized, oh yeah, every 5 years is when the multiplier is applied, right? That's because the exponent becomes 1. So that's just, again, something that's interesting to look at. Okay, we probably won't get to all this, so let's just kind of just briefly talk about it, and then that's fine. And honestly, I don't know if I want to revisit this when we come back from break, because we're going to do a lot of stuff on sequence in the series, but I just feel like we had to have this discussion. Maybe we might do a small quiz on this when we come back. I'll let you guys know. But I didn't test this last year at all, so I don't imagine I'll be testing it this year. But I just want to feel right that you guys have gone through your whole high school, especially you guys being the cream of the crop, the honor students. To never see this, I think would just been a travesty. You guys see this, right? All right, let's just briefly talk about this one here. What are we comparing here? Now, this is a kind of like a chemistry physics example, right? So we're looking at the height of a balloon versus pressure. The height of a weather balloon. This is the height in kilometers, okay? And then the pressure is measured in millimeters of mercury, okay? So, there's a scatter plot, blah, blah, blah. Now, it's increasing, right? Actually, no, never mind. It's decreasing. As the pressure decreases, the height goes up. But the height changes slowly, not rapidly. So it seems like a logarithm would be a good model. And sometimes you have to play with it, right? Sometimes you just plot the data. So they call this exploratory data analysis. Sometimes you just plot the data and just take a look and see what makes sense. Is it linear? Is it quadratic? Is it exponential? Is it logarithmic? It just depends. Apparently, a logarithmic curve would fit this data fine. So sometimes you have to do that. So I'm not going to punch it in the interest of time because we have to go in a few minutes. And I know you guys are eager for the lip syncs. But that's yet another thing we could look at. Or let's look at logistic regression. Now, logistic function does this. This is probably, I think, the best of all the models that we have talked about today. Because what it does, it starts exponentially, and then eventually it flans out. That's more accurate in life. That's usually what happens. So what are we talking about here? We're looking at the population of yeast, I guess, I don't know, in some sort of food or whatever, and through time. Okay, great. So after a certain amount of time, it just levels off. And by the way, this is how this really relates well to calculus. This is why you guys will be so much better off with all the stuff you do in this class. What do you think I'll call that point there? Yeah, it's an inflection point. Correct. Good. It's concave up because there's a sharp increase in concave down. So when I talk about the flattening of the curve during COVID, I kind of say, well, people didn't take COVID, or people who I don't get too sensitive here, but a lot of people didn't know calculus during COVID, right? I just kind of blame that. Like if you understood calculus, you understood what the flattening of the curve meant, right? You understood, oh, yeah, because there's an inflection point. Because when you reach that inflection point, fewer people are getting affected. I mean, fewer are getting infected, but not as a rapid rate, right? The rate starts dropping, and that's what we wanted. We wanted the flattening of the curve. So people stay home, wear your mask, don't get vaccinated, all that stuff, right? Or if you're herd immunity, that you're going that direction. But that's an inflection point, and it seemed like it was happening probably around 8 hours or so. The logistic model would have been a better way to model this data. And you can use it to predict, oh, what do we predict in 19? Because it's not going to keep increasing. It's kind of like, do people keep getting sick at the school? No, eventually everyone gets sick and you're done. And C, by the way, represents what we call the limiting factor. By the way, if X were time, right? What would be my limit as X approaches infinity? Look at this fraction here. If X approaches infinity, and there's a negative exponent, by the way. If X approaches infinity, what do you think happens to this whole term here? E to a negative exponent is going to be close to what number? 0. So then you're multiplying A by 0, which is 0. You're adding 1 to 0, which is still 1. So C over 1 is, of course, C. That's what we call the limiting factor. So now you guys done calculus, right? Now you guys understand. Teach us a couple of years ago wouldn't make any sense to you guys because you didn't learn about limits. Now you know. So you can see how calculus plays a really nice role in this logistic regression model here. This is the best model of all of them I think we've done. Does Desmos do logistic? I don't know. It does. But in the interest of time, we're not going to do it. So, because I think I just kind of got a little too excited about baseball and politics. So, anyhow, talk to any of my good friends. Those are my two things I love. I love politics and sports. So, anyhow, we're all done. Have a good break, guys. No homework. We could maybe talk about this again later, but when we come back, we're going to be focused on sequences and series. It's going to be a pretty intense unit. Just going to warn you guys, but we'll worry about it when we get there. I'll see you guys in 2 weeks.